So we followed the first consequence of the postulate that speed of light is the same in all inertial reference frames. And we followed that consequence by studying the effect that happened when you sent two beams of light in opposite directions. And we found that while the arrival events to the front and end bumper are simultaneous in the frame of the spaceship, and by the way, it doesn't matter if the spaceship is a convertible spaceship or not, because there isn't an ether, so there isn't an ether wind. Speed of light is fundamentally the same in all reference frames. So we found that while those two arrival events are simultaneous in the frame of the ship, they're not simultaneous in any other frame. And I called it the ground frame, but please understand there's nothing special about Earth's ground. Ground is really just another word for any other frame. So that, but you can visualize standing on the ground, right? But there really is nothing special about Earth's ground. Okay, anyway, events, the light beam arrival events are simultaneous in the frame of the spaceship, but they're not simultaneous in any other frame. And we did this with beams of light. But I would like to get across to you the idea that there's nothing special about light. We used light, there's nothing special about light in connection to this relativity of simultaneity. We use light as simply a vehicle to discover this effect that a pair of events that are simultaneous in one frame are not simultaneous in another. What this effect really is suggesting is that time sort of flows at different rates in different frames. In the next lecture, we will explore this in earnest by analyzing a second consequence called time dilation. But before we do that, I would like to elucidate for you why the relativity of simultaneity is really a suggestion that time flows at different rates in different frames. So it's not an effect specific to light. It's really using light in order to discover the idea that time flows at different rates in different frames. That's really the significance of the relativity of simultaneity. So why is it that I'm making this statement? Well, remember that when we looked at Galilean transformations, we had something that looks like x equals x prime plus vt prime, and t equals t prime. So really, we never even write this. We just say x equals x prime plus vt, and it's assumed that time is universal. But I would like you to appreciate this. There is an assumption in pre-relativity physics that while, of course, coordinates transform, of course, right? Obviously, you have a frame, you have another frame. This frame is moving. This is frame S prime. This is frame S. So, of course, coordinates have to transform, right? This is VT. This is X prime. So this is X. Of course, obviously. We never even think about transforming time. Like, why would you do that? So Newtonian physics, classical physics, 19th century physics, 18th century physics, they assumed, they thought of time as something that's universal. In some books, you would talk about Newton's idea of time as this universal clock ticking through the universe. I'm not sure if he actually thought of it like that. He was an interesting fellow. But really, that's what it's implying. It's implying that there's kind of a universal time, background time. Time is its own thing. Space is its own thing. And that's what these Galilean transformations reflect. But you see, relativity of simultaneity throws a wrench into this idea. Why is that? Well, let's go back to our cars, right? So here's a convertible car. And let's say, so here's the emitter. It's emitting these beams of light in opposite directions. Here are the receivers. It's moving with speed v. And let me just label explicitly. So here's the origin of frame S prime, the moving frame. And here is the stationary frame. And as always, I'm going to synchronize clocks in both frames when the origins pass each other. So let's say the origin in the car is in the middle of the car where the emitter is, and the origin on the ground is at some location. And when these two origins pass each other, I'm going to set clocks in each frame to 0. And obviously, as always, clocks in each frame are synchronized, okay? In any given frame, the clocks are always synchronized. And why do we do that? Well, we do that so we don't have to talk of delta t, we can just talk of t, time. Really, time is always a time difference between time and some chosen origin of time. And we chose the origin of time to be that moment when the origins of the frames pass each other. Anyway, we do this procedure. Well, then if we had, if we had t equals t prime, as in pre-relativity physics, then t2 minus t1 between any pair of events equals t2 prime minus t1 prime between any pair of events. Okay, so this is between any pair of events. So 1 corresponds to event 1, 2 corresponds to event 2. In this context, the pair of events is one beam arrives to the front, another beam arrives to the left, to the back. So there are two special events of interest here. A forward moving beam hits the front bumper, a backward moving beam hits the back bumper. And so in particular, if t2 minus t1 equals 0, then t2 prime minus t1 prime equals 0 also. But that's not the case. We saw that as far as the arrival of the two beams to both ends of the ship or spaceship, in the frame of the ship, t2 prime minus t1 prime is 0. The time at which the beam arrives to the front of the ship is the same as the time at which the beam arrives to the back of the ship. t2 prime minus t1 prime 0. But it's not 0 in any other frame, what I call the ground frame.